Hey there, statisticians. In case you missed this lecture in class, I've gone ahead and recorded it for you. This is lecture 4.1, all about scatter plots, and eventually we're going to get into lines of best fit. So just as a short review, a scatter plot is used to compare a piece of data that has 2 points. For example, here we're looking at weight versus horsepower, or weight versus acceleration. So you've got two variables. Usually we say x is the independent value and y is the dependent value. And what a scatter plot is a graphic representation of two variables. So let's take a look at an example. X, again, we said was independent, is going to be the explanatory variable, the what is explaining something to happen. Y is the response. How does something change in response to another variable? So in this example here, this is a data representing the number of hours that students studied and the score that they got on a big exam. So what I'm going to do, let me move myself out of the way. I'm going to go over to the board here and I'm going to call it out and help you set up a scatter plot. So we have to use labels. On the x-axis is going to be the number of hours. Make that a little bit, there we go. So this is number of hours. The y-axis, of course, is going to be the score. Scroll back up, get myself out of the way. Of course, now I need to put a scale on there. You can see my study hours are going from 1 to 7. So let me take it up to 8. So here's 8. Let me cut it in half at 4. 1, 2, 3, 4, 5, 6, 7, 8. So that's just, again, a quick way to eyeball it. You should use a ruler. I'm going to do the same thing on the score axis, on the y-axis for Regents score. Again, I'm going from my lowest value is 40 all the way up to 100. I could use a break here. I could shrink this up and use a break. Or I could plot it from 0 to 100. And let's do that. Either way works. So this is going to be 100. Half of that is going to be 50, and then I'm going to have 10, 20, 30, 40, 50, 60, 70, 80, 90. Oh, it got a little more narrow as I got to the top. Now the next thing I have to do here is just plot this out. So let's go ahead and do it. Again, study hours is x, Regent score is y. So I go to 3 and up to 80, 5 and 90. 2 and 75, 6 and 80, 7 and 90, 1 and 50, I've got 2 and 65, those should be red lined up with each other, 7 and 85, 90, 85, 1 and 40, and 7 and 100. Wow, someone got a perfect. Good for them. So you can see I have successfully made a scatter plot. Of course, the next thing that is often said is, well, draw a line that models this relationship. And if I go ahead and do this, I'll use my little green bar here. I'd say, well, probably, I don't know, it's probably like right about there. And that's the idea of this lesson, of making a line of best fit. What we're going to do in this chapter is take it a step further, and we're going to make this line of best fit a mathematically the best possible line you could possibly have ever. And you can use that to predict values in the future, values below, and of course, anything in between. All right, so what are we talking about here? Data, of course, the data that we just used, it's a line rising from the left to the right, and so we would say that has a positive slope. Well, if it has a positive slope, then there's a positive correlation, and that's where we're going here with correlation and how two variables are related to one another. So correlation shows how dependent a relationship is. It's used in prediction. Is it magic? No, it's right? Fill in the blank. Da-da-da-da. Math. Yep, it's not magic, it's just math. Keep this in mind throughout the entire unit, is that causation is not correlation. Just because two things are correlated, it doesn't mean one causes the other. That usually takes additional study to prove that's the case. And the example, of course, is the weather. We'll talk about that in class. So how do we measure correlation? It's lowercase r, and that's from a sample. If you have the entire population, you use the lowercase letter p, or sometimes rho. But this is on page 136. It's a good idea to open this up and look at it in your book if you don't already know it. But correlation goes from -1 to +1. +1 being a perfect positive relationship, -1 being a perfect negative relationship. 0 means no relationship. And these pictures here, this one shows a correlation coefficient of 0.4, so it's positive. But you can see all the data points are scattered. This is 0 because as you increase the x value, the y values are all over the place. And in this one, as you increase the x value, the y values drop. And you think of that as a negative slope. So other important things to note here, again, pause the lecture if I'm going too fast. Because these values go from 1 to -1, what it really means is as you increase x by 1 unit, if it has a +1 correlation, that means you increase the y by 1 unit. -1 correlation is as you increase x by 1 unit, you decrease y by 1 unit. And 0 means as you increase x, the values go all over the place. And again, when someone says, well, how strong is the correlation? Whether it's negative or positive, the closer the value is to +1 or -1, sometimes they say the absolute value of it, the closer that value is to 1 or -1, the stronger the relationship. All right, so types of correlation. I mentioned PP, perfect positive. Oh my gosh, I got pictures everywhere. I have to get myself, let's see if that works. Perfect positive, high positive, low positive, none, low negative, high negative, perfect negative. Well, let's move these around. So let me grab this one here. This one definitely appears to be some kind of negative correlation, right? That one appears to be some kind of negative correlation. Ooh, this one right here. That is perfect negative correlation. That is high negative correlation. And that one is low negative correlation. Oh, wait a minute. This is perfect positive correlation. This is high positive correlation. And I bet this one's sneaky back here. Oh, sneaky. Is low positive correlation. And of course, this one here, the points are all over the place. I really can't draw a line. If I drew a line, might as well be horizontal. It's just going to cut right through it. So anyway, I hope that gives you a better sense of perfect positive, high positive. Values are close together, but they're not make a perfect line. Low positive, they're spread out, but they're still generally going up as you move to the right. Perfect negative, for every 1 you go to the right, you go down 1. High negative, again, they're pretty close together, but there's some spread. And then low negative, they are generally going down, but spread out. Okay, again, correlation ranges from -1, oh, that's awful, to +1. And just keep this in mind, there are multiple kinds of correlations and regression. This unit we're focused on linear. There's quadratic regressions, there's exponential, there's polynomial, you name it. There's all sorts of different kinds of regression. In this one, we're talking about linear regression. Hey, so if you need to take a break, now's a good time to do it. Hit pause and welcome back. What we're going to do now is actually calculate the Pearson product correlation coefficient, also just known as R, correlation coefficient. And when you look at this crazy formula, don't freak out. You just need a few pieces of data and we can do this. So you're going to start by making a table. This is an example. Again, I've got 4 data points. So n is 4, right? 1, 2, 3, 4 data points. Each point has an x and a y coordinate. And what we need to do is we're going to get a lot of sums of things. So again, when you look at this formula, it's not so bad. It looks really crazy. It's not. The number of values times the sum of the x and y values multiplied together. The sum of the x values multiplied by the sum of the y values, the square root, etc., etc. So we're going to go through this. And yeah, let's just go through it. All right, so the bottom one here. The sum of the x values means to just add up these values. 4 plus 4 plus 3 plus 1 is 12. 2 plus 8 plus 5 plus 5 is 20. And again, I'm going to sum y, and I get 20. Now I'm going to square these values. So x squared means 1 squared is 1. 3 squared is 9. 4 squared is 16. 16. Now I'm going to sum them up. The sum of x squared equals 1632, and 10 is 42. Next one here, the sum of the y values. 2 squared is 4. 5 squared is 25. 25, 64. When I add these up, 68 and 50 is 118. Sum of y squared equals 118. Finally, multiply x times y. 1 times 2 equals 2. 3 times 5 equals 15, etc. down. 4 times 5 is 20, and 4 times 8 is 32. When I add these values up, 17, 9, 50, 60, 69. This is the sum of x times y. Now I've got all the pieces of data. Now I need to actually plug them into this formula correctly and then be very careful when I do it on a calculator. All right, I've moved myself out of the way. Let's go ahead and do this. I know my n is 4. So let's bust it out. I've got 4 times the sum of x times y is 69 minus the sum of x, which is 12, times the sum of y, which is 20. All of that over the square root of 4 times the sum of x squared is 42 minus the sum of x squared multiplied by, and again, same thing, 4 times y squared, 118, minus the sum of y squared. And that's it. So here's what I'd like you to do. There's the formula. All the numbers are plugged in. Go ahead and try it on one of my blue calculators or at home, and then see if you get the following answer. Okay, welcome back to Mr. Rising's Talking Mouth. You want to see, did you get the right answer? Well, first of all, here's our original formula. I just plugged everything in, wrote it out. And then I simplified things down, scrolling up, right? 276 minus 240 over those differences square rooted. When I simplify that further, you get 36 divided by the square root of 24 times the square root of 72. And of course that equals 0.866. In fact, if I was just so crazy and I wanted to verify that on my calculator, I could. And I'll show you how to do that too next time in class. All right, the last thing we need to talk about, of course, we'll go over this example some more in class and we'll practice it, are something called a lurking variable. And please take a look at page 143. You've got a number of questions that you need to practice that involve a lurking variable. But the idea of a lurking variable is something that causes a change to both x and y. So it may look like there's a correlation between two things, but really there's something that's causing both the x and y value to do something, and really x does not have an impact on y. And we'll go through examples like that. Those are some of the problems that you have to do in section 4.1. Hope this was helpful, and look forward to seeing you next time.